Okay, good afternoon. Want to get started? So I just want to talk a little bit about last time. Oh yeah, so I'll mention, as I announced on BSpace, I won't be here the week after spring break. Either I'll have just had a baby or be about to have a baby, so either way. Not me personally. I recognize that sometimes happens. Thank you. Thanks, that's very sweet. Okay. Yeah, so back to statistics, and okay, everyone fine with that? So as I mentioned, Roger Purvis will be taking over those lectures. He is one of the authors of the book. I mentioned on BSpace, if you want to, you can see what he has to say about it. If you want to, you can also look at my archived webcast lectures from last spring. And in the BSpace announcement, I say which lectures you could look at if you want. Last spring, the lectures were Monday, Wednesday, Friday, so it doesn't quite match up exactly, but basically, more or less, there are 3 lectures from last year that correspond to 2 lectures from this time. Okay. Yeah, so I'll say one more thing about that, which is that I usually skip around a little bit in the book after I hit chapter 18, and I'm skipping around a little bit differently than last year, and that's why the lectures aren't sequential. The ones that I'll have you look at, if you want to look at them from last semester or last spring. And also, I felt like the lectures that I want someone else to give, it makes more sense to have those lectures be on chapters 20 and 21 rather than on chapter 19. Chapter 19 is a little bit analogous to chapters 1 and 2. It's sort of stories and examples, and I sort of want to do that myself. So he's going to do the more mathy chapters 20 and 21, which are, I think, makes a little more sense to have him do it. It'll be closer to what I would say anyway. Okay. So back to chapter 18. So my plan for today is to finish 18, and I'll talk just a little bit about 19, because I think it's sort of interesting to talk about 19. And then I'll see you in 2.5, 3 weeks. Okay, so there's this thing about chapter 18 that as the number of draws increases, the probability histogram for the sum of draws gets closer to the normal curve. Okay? There's a theorem called the central limit theorem. I don't care if you know the name of the theorem, but I would like you to know that such a theorem exists. There's a theoretical reason why this is true. I feel like on some level I'm just asking you to trust me about this fact. And like I said before, I think this fact is a little bit surprising, that it doesn't really matter what you start with. You can start with any kind of weird box, die rolls, coin tosses, whatever. And eventually, if you increase the number of draws enough, you'll get something that looks pretty close to the normal curve. So I'll do a couple of examples where this, I won't say it fails, but it doesn't do so well. Okay? Last time I did a couple of examples with coin tosses where it works very well, where the normal approximation is very exact. So I'll do a couple today where it's not so exact. Okay, so first one I want to talk about is this. So I've labeled this as it relates to the binomial. N is 10 is like the number of trials. P is 0.5 is the probability of success. Thanks. So you can think of this as like binomial with 10, n equals 10, p is 0.5, or you could think as like number of heads in 10 coin tosses. Think about it a little bit more intuitively that way. So last time I showed you some pictures for coin tosses for I think 100, 400, and 900 coin tosses, which is in the book. For all those cases, they look pretty good. This one is not awful, right? It's sort of, the curve sort of follows the bars fairly closely. But if you remember from last time, if you don't, I'll remind you. I said that normal approximation is okay, meaning for like exam purposes, when, first of all, at least 25 draws. And second thing to check is that expected value plus or minus 2 SEs is in range of possible values. Okay, so this fails, right? Number of draws from this box would only be 10, so it's not at least 25. So officially, we're judging this as a normal approximation is not accurate enough for our purposes. I'll do a calculation with a normal approximation, and you can also see by the picture that normal approximation is not going to be awful, right? The curve is not that far from the bars. Remember, the bars represent kind of the truth. The area of each bar is the actual chance of that thing, that number of heads, whereas the curve is an approximation of that. Okay, so I made this picture for 10 coin tosses. This is 100. This is like one of the pictures last time, like the top picture last time. It's pretty good here. And then I did it for 1,000. Okay, so you can sort of see that this statement is true, right? As we increase the number of draws, meaning coin tosses in this case, we get something closer and closer to the normal curve, right? So normal approximation is going to be very, very good in this case. Pretty darn good here too, and I did a couple of examples calculating the chance of exactly 50, that bar in the middle, and also 45 to 55 heads. I did both of those on Tuesday. And then this one, I'll do one example of this, and you'll see that it's still pretty accurate, but just not quite as accurate. Okay? Alrighty, so let's put that up and lights. Okay. Oops. There we go. Okay. So what I can do is I'm going to find the chance of getting exactly 5 heads in 10 coin tosses. So it's the center bar from that picture that just went up. So again, like last time, I'll do this in 2 different ways. The first way is purely from binomial. So this is 10 factorial over 5 factorial, 5 factorial, 1/2 to the 5th, 1/2 to the 5th. Okay. So it's like 5 heads, 5 tails, and then all the ways of mixing that up. And oops, this comes out to be 0.2461. Oops, 2461, or if you want to do it in percentage terms, 24.61%. So if we do normal approximation for this, we're talking about a box for counting the number of heads. So it's zeros for the tails, ones for the heads. We have 10 draws. And I did all this stuff last time, so I won't talk about it too much, but average that box, just add them up, divide by how many there are. SD of that box, I'll write out the shortcut. It's quick. So we have big thing in the box. This is the shortcut for calculating SD that I did last time. Big number in the box minus the small number in the box times the square root of fraction of big ones, so fraction of ones times fraction of zeros. So that comes out to be 1/2. Okay. So that's a shortcut in chapter 17 of calculating the SD when there are only 2 kinds of numbers in there. Okay, so then expected value for 10 draws is number of draws times the average of the box, comes out to be 5, and the SE is the standard error for the sum of draws from this box, meaning like counting the number of heads. Square root of the number of draws times the SD of the box comes out to be 1.58. Okay, so now I'm just going to sketch the picture. Oops. 5, 6, 7, 8. Okay, so something like this. So these dies off a little faster. Okay, so normal curve looks something like that. So what I really want, right, what I found up here is the area of that bar. Okay, so this 24.61, you can think of like there's a bar at 5, and it really is truly the area of that bar. Oops. Here I'm doing normal approximation. So what I want to do is think about the area under the curve between these edges. So area under the curve between 4.5 and 5.5. So this right edge is going to be 5.5 minus the expected value 5 divided by the standard error, 1.58. Comes out to be 0.316. And this left edge is 4.5 minus expected value 5 divided by standard error of 1.58. And that comes out to be negative 0.136. All right, so that's not on your normal table exactly. If you were going to do it on your normal table, you'd find the area between minus 0.3 and 0.3. So you'd look up this. And you'd find that that area is 23.58%. 23.58%. Okay. So that's off by about 1%. We can do a little bit better if we have a more detailed normal table or if we use a computer to figure it out. So I did. And if you actually, you couldn't do this, but just for purposes of seeing how accurate the approximation is, I went ahead and looked up what is the real area between those 2 points. And it's 24.82. Okay? You can see it should be bigger, right? This area is going to be bigger than this because this, sort of rounded down. Okay, so this is pretty close, right? 24.61 compared to 24.82 is off by about 0.2%. If you remember from last time, my answers were off by like a couple thousandths of a percent or something like that. So my answers last time were or maybe even more accurate. So this is not too bad, but with more draws, you get much more accurate results. Okay. And one reason why I've adopted this rule of using normal approximation only when at least 25 draws, it is sort of arbitrary, right? As we increase the number of draws, our approximations are going to be more and more accurate. They're going to be closer and closer to what the binomial would say. So that 25 draws is kind of arbitrary. It's part of the reason why I chose that is just that I sort of have to choose something, and it's a point at which it's sort of pretty accurate. Okay, so it's sort of there's no particularly good reason to choose one value instead of another. Yeah. So any questions about this? Yeah. Question is the normal approximation always bigger? No, in fact, it's always bigger than the binomial answer. It can't be because the total area for each one has to be 1. So if it's bigger some places, it's going to be smaller other places, right? Nearer the center, I think all my examples have been in the center. I'm not right at the center. I guess both of them were bigger, but I'm not sure if there's any real reason why that should necessarily be true. So yeah, it could be bigger, could be smaller. Okay, any other questions? Okay, so this is one that sort of officially it fails because it's fewer than 25 draws. With more draws, you get a better answer. I want to do an example that fails because of this now. Okay? So I want to take 100 draws from this box. Sorry, take sum of, I'll say it this way, take sum of 100 draws from this box. So I'm just setting that up as my box model, 100 draws, and take the sum of that. So this is more than 25 draws, right? So the first part of the thing where I want to check for it works. It's at least 25. You might be a little bit suspicious when you see something like this that something might go wrong because it's so lopsided, right? It's so skewed. we have something, we have a nice box here at least, even though we don't have very many draws. The 0, 1 kind of guarantees that things will at least look symmetrical, right? Like the chance of 7 heads is the same as the chance of 3 heads, because 3 heads means 7 tails, right? So, you know, those 2 bars should have the same height. Those 2 bars should have the same height. Nice symmetry there. You're not going to get that in this case, and because it's so lopsided, you should be maybe suspicious that it won't look so nice, right? So I'll show you a picture of it in a bit after I do the math. So average of this box, if we add everything up, divide by, oh, I'm sorry. Let me say what my problem is. I want to find the probability of 0. So the sum of the draw, to find the probability the sum of draws is 0. So essentially, I want to find the probability that I never draw that 1. I take 100 draws, and the 1 never comes up. Okay, so the average of this box is add them up, divide by 100. And the SD of this box, I'll use the little shortcut thing. Big value is 1, small value is 0, times the square root of fraction of 1s is 1 over 100. Fraction of zeros is 99 over 100. And this is very close to 0.1. 1 minus 0 out in front. And this 99 out of 100, that's pretty close to 1. 1 over 100, take the square root of that, we get 0.1. So it's pretty close to 0.1. Okay? So the expected value is number of draws times the average of the box. So that's 1. That's pretty intuitive, I think, right? If you take 100 draws from that box, you expect the 1 to come up about once. And the standard error, square root of the number of draws times the SD of the box. Square root of 100 is 10 times 0.1 is 1. Okay? So when we make that second check, it says expected value plus or minus 2 SEs is in the range of possible values. Well, what's possible? In theory, I could get anything from 0 to 100, right? And 100 draws out of this box. The number 1 could come up anywhere between 0 and 100 times. So 0 to 100 is the range of possible values. I go 2 SEs to the left of the expected value. I get negative 1. That's not possible. So that's failing. That check is failing. I guess I'll just mention as an aside, that check was OK here, right? Take 5, go plus or minus 2 SEs. You're still between 0 and 10 at least, OK? So although this fails because it's not enough draws, it's OK in terms of the second check, right? So 2 SEs to either side of 5. Here, still in the range of possible values. Here, it's not. OK, so normal approximation is not going to be that good. I'm going to go ahead and do it anyway and sort of show you how bad it is. So what answer should I get if I don't do normal approximation? You don't have to tell me a number, just how would I do it, or how would I calculate the chance of never drawing the 0 in 100 draws? Anyone want to do that? Answer that? Anyone? You could use binomial. I think there's a slightly easier way to look at it. So the suggestion is to use the complement. I think the complement is going to make your life harder rather than easier. I want to find the chance that the 0 never comes up.
1 over 100.
Yeah. That would be if you want to get a sum of 100. He said 1 over 100 to the 100th power. In that case, the sum of draws would be 100. Right? I want to find the chance the sum of draws is 0. It's sort of the right idea. Yeah?
Can you do 99 over 100 to the power?
Yeah, 99 over 100 to the 100th power. Right? You have to draw the 0 the first time, draw a 0 the first time, and the second time, and the third time, and 100 times, right? So, what's that? Yeah, I'm always assuming the draws are with replacement for box models for now. Okay? It sort of has to be for this case, right? If I didn't do this with replacement, I would just draw all 100 tickets, and I would get, the one would come up once. Right? Yeah, so with replacement. And yeah, so until I get to sort of the end of chapter 20, I'm always going to be talking about draws with replacement. Okay? Okay, so 99 over 100 to the 100th power. And I'll write that as a binomial. I'll write out, if you just sort of blindly use the binomial, what would you do? You would do 100 factorial over 0 factorial, 100 factorial. 0 factorial, I don't know if I ever mentioned that. That's 1. Okay? That's not 0. Okay? And that I have 99 over 100 to the 100th power times 1 over 100 to the 0 power, okay? Which is just this. Everything else goes away. 99 over 100 to the 100th power. And that comes out to be, I think, 0.366. Yeah. Or about 36.6%. Okay. So now, if I do normal approximation for that, I got my expected value, I got my standard error. It's going to look like this. And it's centered at 1. There's 0. There's 2. And I'm just going to draw on here. I'm not going to draw any bars for the moment. I don't really know what they're going to look like. But where I am here is here. So there's some bar here. I don't know how high it is. But there's some bar here, and what I want is the area of that bar, right? So if I think about a normal curve centered at 1, SE of 1, that maybe looks something like this. Okay? Okay. So I'm sort of being a little bit vague about what this bar is. I don't know how tall it is. Maybe it's taller than that. Maybe it's shorter. But to find the chance of, like, actually, let's do it this way. To be concrete about what I'm finding the area under the curve between minus 0.5 and plus 0.5. Okay, so minus 0.5 in standard units minus the expected value divided by 1 is minus 1.5. So that's this left edge. Minus 1.5 is this. And then this right edge is plus 0.5 minus the expected value of 1 divided by the SE of 1 gives me minus 0.5. Okay? So in standard units, I have minus 1.5 plus 1.5. So this is not nice and symmetrical, so I need to think about this a little bit. So if I look up minus 1.5 on the table, excuse me, look up minus 1.5, I get 86.64 in the middle. When I look up minus 0.5 to plus 0.5, I get 38.29. This is 38.29. And what I want is like this part, right? This part here. So to get that, what I'm going to do is take the big area of 86.64, subtract the middle area of 38.29, and then divide by 2 to get just this part here. Okay, so 86.64 minus 38.29 divided by 2 is 24.285. Okay? So that's my normal approximation answer. So it's pretty bad, right? The binomial, like the right answer, is 36.6. So now I can tell you what that bar looks like, right? It's taller. You know, it's maybe something like this. Okay? The true area of the bar is 36.6%. Sorry, here, 36.6%. The approximation under the curve is, you know, about 24.3%. So this bar is quite a bit bigger. Okay, so let's think about a little bit why that's true. And then I'll show you a picture. So let's see. That. Well, I'll just put that down for a second. I'll talk while that's coming down. So there's nothing to the left here, right? There aren't any bars out here. However, the normal curve continues. So that's essentially what's wrong. Now you notice the check that we made was to check expected value plus or minus 2 SEs. when we go 2 SEs to the left, the normal curve says there should be something there, okay? And in fact, there isn't. So this is our check to sort of recognize that there's something going wrong, that the normal curve is going to have area out here, but in fact, there shouldn't be any area out there. So what really happens then is that we have something like this going on. Okay? This one bar, this picture should balance at 1. The expected value is 1. So somehow this one bar over 0 has to balance everything else. Okay? So this bar must be pretty tall. Okay, so without doing the calculation, without knowing that this bar has to be higher, we could kind of use that logic to see that it probably should be higher, because somehow that one, like I say, that one bar has to balance everything else to the right in order for this thing to balance at the expected value of 1. Okay? All right, so let's look at the actual picture. Oops. Get a blank piece of paper there. Okay? So that's what it looks like. And I didn't continue the normal curve to the left there, but you can see that that first bar is quite a bit larger. So actually, I should draw this a little bit better. I guess it looks a little bit like this, right? Okay? So this dives down pretty fast here. Okay? So something like that. These first two bars are about the same height. I guess the second one's actually just a tad bigger. Okay? But anyway, the idea here, though, is that normal approximation works quite badly here. And that bar over 1 actually is not horrible. The curve is above it, but it's not horribly above it. The second bar, the bar over 2, is pretty bad. The curve is a lot higher. For 3, it's maybe not too bad. The area above and below the bar is about the same. But in general, we don't have any way of being confident that our answers from normal approximation are going to work well in this case. Okay? So, yeah, rule of thumb is don't do it if expected value plus or minus 2 SEs get you in some area that isn't possible. So here, 2 SEs to the left, -1, not going to work so well. Okay? So I did, my claim is that as we increase the number of draws, eventually we should get a probability histogram that looks pretty close to the normal curve. Okay? 100 draws maybe isn't enough here, but if we increase it to 1,000, we're getting pretty close. It's still, the bars on the left are taller than the curve. And the way I should really say that is that the curve is smaller than the bars, because the bars are right? The bars represent the true area. There's a tendency here to look at this picture and think, oh, the bars aren't matched up right with the curve. But it's not really the bar's fault. The bars are telling the truth. It's the curve that's wrong, right? So the curve is constrained to be nice and symmetrical in this particular shape. And in reality, the probabilities aren't following that form, okay? So the probabilities are right, the bars are right, the curve doesn't approximate it so well, okay? As we get to 10,000, it's still true that the curve is a little bit below the bars on the left, the curve is a little bit above the bars on the right, but it's pretty darn good, right? So your answers here might be off by a little bit, but should be pretty accurate, even though we started with this pretty lopsided, crazy box, right? So if we continued, I didn't do any more pictures, but if we continued, you should expect it to get even more accurate. Okay? Any questions? Thoughts? Okay, so let's see. Let's see anything else about that? Okay, so that's one example of each of the ways it fails. That's a pretty good time for a break, even though it's a little bit early. So let's take a little break, and then I'll finish up the last bit of chapter 18. One second. I'm done with all the pictures, so just so you know. Yeah.
This, if we compare the
Okay, why don't I get started again? So like I said, I wanted to finish up chapter 18. Chapter 18 is kind of long. And then I'll spend just a little bit of time talking about chapter 19. Okay, so I've done the normal approximation stuff. I've talked about like when you use normal approximation, when you shouldn't use normal approximation. The one part, the one subtle thing that I haven't talked about is when to do this plus or minus 0.5 thing, right? So you have discrete probability histogram here, and the edges of the bars are at plus or minus 0.5, okay? So I want to be a little bit more concrete about when that should happen. So that's called the continuity correction, sometimes called taking care of endpoints in your book. Taking care of endpoints. And so what this means is, going plus or minus 0.5 from centers of bars to get the edges of the bars, or to find edges of bars. So I've actually used this, I think, on every example I've done so far, right? Finding the chance of exactly 50 heads, finding 45 to 55 heads inclusive, including those endpoints. Those are the examples I did on Tuesday. And then today, 5 heads out of 10 coin tosses. I needed to use, again, the edges of those bars, 4.5 and 5.5. And then this last example, the area of the bar over 0, normal approximation tells me I should, again, go plus or minus 0.5 to get the edges of that bar. Okay? So in general, I'll give you some rules. So use for a discrete probability histogram and that's pretty much what we're dealing with now is discrete probability histograms. Once we get into chapter 20, we'll start talking about continuous probability histograms. So you just think about the data we looked at the beginning of the class, could be the discrete or continuous. When you're talking about the numbers of things, like numbers of heads in this case, if you're talking about data, you might talk about like number of pets or siblings or something like that. Continuous is more things like age. We did the monthly cell phone usage example with minutes, things like that. Okay. So for now, all these examples I've done are with coin tosses, so we're talking about the number of heads. That's discrete. Okay, so that's used for discrete probability histograms, probability histograms when, first of all, you have clear language. Actually, I'm sorry, I want to do another one first. Sorry. Talk about language in a second. The first thing I want to say is you have consecutive integers in the box, sort of whole numbers in the box. Okay. So in order for it to be discrete, you really have to have this situation. You have to have whole numbers. They might or might not be consecutive, and I'll say in some depth why this is important. The maybe quick way to explain this is that there are no gaps in the histogram. Okay? So all the boxes I've talked about so far are just 0, 1 boxes. Those are consecutive integers, and there are no gaps. So what I mean by that is like in 100 coin tosses, you could get 48 heads, you could get 49 heads, you could get 50 heads, you could get 51 heads. If for some reason it were impossible to get 51 heads, if you had a gap there, there's no bar there, then it doesn't really make sense to use continuity correction. Okay, I'll do an example that kind of illustrates that. But for now, just this is a rule. You have to have consecutive integers in your box somewhere in order to do this. So what I mean by that is like so use for a box like 1, 2, 9, but not -1, 1. So all the numbers in the box do not have to be consecutive. 1 and 2 are consecutive, and that's enough. Again, I'll talk about why that's true in a little bit. This is not consecutive, right? So if you draw from that box, you're going to have a problem because you're going to have gaps in your histogram. And again, I'll give you an example of that. OK, so let me get through the rules. I'll come back to this. So second thing is clear language. And I'll just say for exam purposes, this is really the only thing I care about. I'm never going to give language that I consider to be unclear on an exam. The book sometimes, so the book goes through this example of 45 to 55 heads in some detail. And they do it 3 ways. The first way they do it is inclusive, including the endpoints. And that's the same example as I did on Tuesday. They also do it exclusive, meaning excluding the endpoints. So if you do it exclusive, exclusive means 45 to 55 heads exclusive means you don't want to include the bars over 44 and 55. So to exclude them, you would use 45.5, the right endpoint of the bar over 55, and the left endpoint of the other bar. So 45 is here, 55 is here. I don't want to draw all this, but excluding, you would take the inner parts of the bars. So 45.5 and then 54.5 would be the right edge, okay? Or I guess the left edge of the rightmost point. The book does it a third way where they just say, find the chance of getting 45 to 55 heads. And what they say about that is that it's sort of vague. It's unclear whether or not you should include them or not. So just go ahead and use the centers of the bars, okay? I think that's a little bit, I wouldn't want to do that on an exam. You give something that's sort of unclear whether or not you should include the bars. So on exams, I will say exclusive, inclusive. I might use slightly different language. I might say like, find the chance of getting 60 heads or more. That clearly includes 60, right? 60 heads or more includes 60. So that tells you whether or not you should include that bar. But somehow, somehow the language should tell you what to do. OK? But like I said, that's mostly an issue the book discusses for exam purposes. I won't try to trick you in that particular way. OK. And the last one is that it's sort of optional if number of draws is very large. So you notice in the pictures that I've shown you, as you increase the number of draws, the bars get really skinny. Okay? All these series of pictures I showed you of probability histograms, the bottom picture has like these really skinny bars. Well, basically, if the bars are really, really skinny, each bar has very little area. So it doesn't really matter that much if you go plus or minus 0.5. You're talking about including half a bar or not. And those bars are so skinny that it's not going to change your answer very much. So very large, I'll say like at least 10,000. So again, you don't really need to know this. These 2 last ones for taking, the final, you don't really need to pay attention to them. But when you read the book deals with these sometimes. So there's one example in the book where they don't do it, and it's like 10,000 coin tosses. And so I'm basically including this so people don't ask me about that example. Why didn't they use it? Well, it doesn't make much difference if you use it or not, so that's why. OK, so that's that. Those are my rules. OK, so let's talk a little bit more. Any questions? I'm going to talk more about the first one. So if you have questions about that, maybe wait until I do the example. But any other questions? OK. So I want to do an example with roulette. So like last, I guess maybe 2 lectures ago, I talked about roulette. Maybe it was last time. I guess it was last time. Find chance of winning money in 100 bets on red. Okay, so if you remember, bet on red, there are 18 red slots, 20 non-red. Spin the wheel, the ball lands in some slot, and if it's red, you win $1. If it's not red, you lose $1. Okay? So I guess I didn't really say all that, but this is a continuation of a previous example. So win $1 if red, otherwise lose $1. Okay. So one more thing I'll just say for clarification. When I say winning money, means net gain more than 0. Okay? I'll say it in English. More than 0. Okay? So net gain is like the sum of all the dollar amounts. It's how much you walk away with should be positive. Okay? Questions about the setup of that? Okay, so the box is the same as I did before. Either you win $1 or you lose $1. So the numbers in the box are going to be positive and negative 1. And there are 18 ways to win $1, 20 ways to lose $1, 100 bets. Okay? So you sort of maybe check that the chances come out right. They're, like I say, 18 reds, so 18 chances to win $1 out of a total of 38 slots. So the kind of probabilities come out right. Okay, so then I won't do all the math again. I'll do a little bit of the math again. If you add all these up, and divide by how many there are, it's like 20 negative 1s plus 18 1s divided by 38. This comes out to be minus 0.526. And SD is 1 minus a negative 1. The big number in the box minus the small number in the box. Square root of fraction big times fraction small. So fraction of 1s times fraction of negative 1s. And that comes out to be very close to 1. And then expected value for the sum of those 100 draws is 100 times minus 0.526. Oops. 526. So that means that in 100 plays, you should expect to lose about $5.26. I'm sorry, there's another 0 there. Sorry, there's I left out a 0 there. This is 0.0526. 0526. Okay. So 100 times that is minus 5.26. Like I said, you lose about $5.26 in 100 plays. And the standard error for the sum of draws, square root of 100 times 1 is equal to, square root of 100 is 10 times 1 is 10. Okay? So we play 100 times. We expect to lose about $5.26, give or take about 10 bucks. All right. Questions about that? That's all stuff I did before. Now, when we do normal approximation, if we think about our checks to make sure normal approximation will work reasonably well, at least 25 draws. That's fine. We have 100 draws. And then expected value plus or minus 2 SEs. Well, what's the range of possible values here? What's the worst thing that could possibly happen to us? 100 plays. You lose them all. You lose $100, right? Lose every time, you lose $100. If you win every time, that's the best you could do, you win $100. So the range of possible values is somewhere between minus 100 to plus 100. Expected value plus or minus 2 SEs is fine. It's well within that range, right? So it passes our 2 checks. It's minus 2 SEs is about minus $25, plus 2 SEs is about plus 15. So yeah, expected value plus or minus 2 SEs is well within the range of possible values. Okay, so normal approximation seems fine. So I'll go ahead and draw the curve. And we have centered at the expected value of minus 5.26. So this axis represents net gain. Out here somewhere is 0. So essentially I want to find this. I want to find the chance that the net gain is more than 0. Okay? So when you think about whether or not I should draw a bar there and find the left and right edges, well then you come to this, we want to use the continuity correction, do this plus or minus 0.5 thing for a discrete probability histogram. And this is discrete, right? They're whole number values, but the numbers in the box are not consecutive. I just have negative ones and ones. Okay? So this fails. So I'm not going to do continuity correction. I'm just going to use the center of this bar to do this. And after I do the calculation, I'll explain why. But just if I just sort of blindly follow the rules, I want to find the area to the right of 0. So in standard units, that's right at the expected value. So that's 0 in standard units. This one is going to be 0 minus the expected value divided by the standard error. So that comes out to be plus 0.526. All right, so when you look that up, find the area to the right, you get, this is almost halfway in between two values from the table. So it's about halfway in between what I would get for 0.5 and 0.55. So I'm going to just, if you look up 0.5, you get, let's see if I have one. I didn't write down the exact. So yeah, if you look up 0.5, you get 38.29. If you look up 0.55, you get 41.77. 38.29, 41.77. About halfway between is 40. Okay? So I can say this is about 40. Okay? If you used if you looked up 0.5 or 0.55, I guess looking at 0.55 is slightly smarter. This is slightly closer to 0.55. But yeah, if you use either one, I don't think I would take off any points. So if you look up, if you do it then, you get about 40 in the middle. Area to the right is about 30%. Okay? So the chance of winning money in our 100 plays is about 30%. Okay? So questions on that? Okay, so let's talk about this continuity correction issue. So is it possible for us to break even? To walk away with exactly the same as what we started with in 100 plays? Is that possible? How could that happen? What would have to happen in the 100 plays?
Win as many times as you lose.
Yeah, so you win 50, you lose 50, right? So when you think about truly what is the probability histogram look like, there is some chance of coming out with exactly 0. So if win 50, lose 50, net gain is equal to 0. Okay? So it's possible that I could exactly break even. Is it possible for me to win exactly $1? Yes? No? How can I win? Someone's saying yes over there. How can it happen? If I, oh. Right, so if I win 51 and I lose 49, then the net gain is $2, right? Okay. So there's no way for me to win exactly $1, right? So what's going on here is that if you think about what the probability histogram truly looks like, you have a bar over 0, you have a gap, you have no bar over 1, and then you have a bar over 2. Because the area of these bars should represent the chance of that particular thing happening. Okay? So what I'm going to draw on this board, I don't really care if you know. What I care about is you being able to follow the rules. Okay? But I do feel like I owe it to you to explain why that rule exists. And if you think about what's going on then, how would we do this? Like, we're centered at minus 5.26. There's a bar over here at 0. And then there's no bar at 1. There's a bar at 2. It's probably smaller, right? And then we're going like this. Well, why does normal approximation work here at all? Because the normal curve doesn't do that, right? So if you think about trying to match this up with the normal curve, well, your first thought might be that you want to do something like that. You want to sort of hit the bars. But that doesn't really make sense because the total area under the curve is 1, right? 100%. The total area of all the bars is 100%. And clearly that doesn't work, right? Because there's all these gaps. So that if you added up the areas of all these bars, it shouldn't match up with the area under the curve. So what you really should do if you want to do normal approximation in this case, well, maybe you should do this. There are bars at every other place, so maybe that makes some sense. But that sort of doesn't look so good, does it? So if you really want to sort of, I don't know, make your picture match the curve and have things sort of look reasonable with the bars centered at the values, well, really, maybe what we should do is this. Keep it centered at 1, but make the edge of the bar, there's a bar at 0, there's a bar at 2, and make the edge of the bar halfway in between, okay? So I think, trying to draw the picture, maybe I would do that, and then the curve matches the bars pretty closely, and everything would look good, but the edges of the bars are not at plus or minus 0.5, right? So rather than trying to make you deal with this and figure out where the edges of the bars are, I'm just saying ignore the whole issue and just pretend like it's continuous, like I did here, right? Just, don't even worry about drawing in the bars. Just find the chance that it's more than 0, okay? And don't worry about where the edges of those bars are. This is a little bit of, this example is actually fairly simple. What if I did, so if you bet on a single number on roulette, bet on a number, your box looks like this. You have 37 tickets marked -1. There are 37 ways to lose $1. And the way roulette works, you don't need to know this. If you win $35, okay? So if this is your box, and you attempt to draw a probability histogram, well, what's going to happen? With the -1s and +1s, if you like switch a 1, if you like get 1 extra win here, you win $2 extra. Because your wins go up by 1, your losses go down by 1. So you end up with $2 more. Well, in this situation, if you win 1 extra time, you jump $36, right? You get 1 extra win, you get 1 fewer loss, so you jump $36. That means that there are huge gaps here. There's a gap every 36 there's a bar every 36 numbers. So if I told you to do this and somehow try to work out where the bars are and where the edges are, it's pretty mean, right? So that's what I'm trying to avoid, okay? So again, you don't need to know this. I would like you to understand the basic idea that having consecutive integers in the box guarantees us that we have a bar over every number. Okay, so 1, 2, 9. Well, why does that work? Well, if you sort of think about the same idea as here, can you have a net gain of 0? Yes. Can you have a net gain of 1? No. Next net gain is 2. What if I have a sum of draws from this box? Well, first of all, it's got to be at least 25 draws for me to even think about normal approximation, right? So if I have 25 draws from that box, presumably I'm going to get some 1s and some 2s. If I drew 1 extra 2 and 1 fewer 1, that would give me a bar next door, right? So wherever you have a bar, you also have a bar 1 to the right. You also have 1 to the left if you took away a 2 and added in a 1. So you can sort of see that if you drew a probability histogram for draws from that box, at least you get a bar everywhere, okay? And that's actually done as an example in the book, and it's not, it doesn't look so pretty. It doesn't look exactly like the normal curve because it's a little bit lopsided with that 9 sticking out there, but at least you have a bar over every number, okay? So the normal approximation should look reasonable. For these cases, -1, 1, you have these gaps. With this, it's pretty awful where the gaps are. And so I'm just saying for these cases, let's just sweep the issue of continuity correction under the rug and just pretend like it's continuous. Okay? So any questions on that? Yeah? Yeah, so if you bet on a single number in roulette, you either win $35 if your number comes up, or you lose $1 if your number doesn't come up. So yeah, this is done in your book. I don't want to belabor it, but just sort of think, if this was your box, you can see that if I got an extra 35 and one fewer one, there's going to be a big jump. That's really my point of putting that up there. Okay? So, questions about continuity correction, any of those issues? Okay. I feel like that rule seems a little bit like, I don't know, some kind of semantic legalese kind of thing to sort of work it out that way. I'm actually trying to make your lives easier by doing that rather than trying to deal with this. Alrighty. So, let's talk about chapter 19. That's the end of chapter 18. Let's talk about chapter 19 a little bit. So, chapter 19 is about sampling. So I want to kind of give this kind of big picture idea about what we've done so far. So chapters 17, 18, and also 20. Of course, we haven't done chapter 20 yet, but all three of these chapters deal with the same basic idea that you have some, if you have some probability thing going on, like number of heads in 100 coin tosses, the actual number of heads in 100 coin tosses should be somewhere around the expected value. But it might be off because of chance error. So a lot of what we're doing in chapter 17 and 18 is calculating these things, right? We're calculating the expected value directly, and we can't calculate the chance error because it relies on something random happening, right? Like Karich got 44 heads out of 100 coin tosses. So for that particular case, the chance error is -6. He got 44 heads. He would have expected 50. So his chance error is -6. We can't, in general, know ahead of time what the chance error is going to be, but we can talk about the standard error. Right? The standard error measures the likely size of the chance error. Okay, so that's like a 2-line summary of what's going on in chapter 17 and 18, I guess. Or I guess that's mostly 17. 18 really does more with normal approximation. So chapter 19, and to some extent chapter 21, thinks of this in a slightly more real-world setting, less probability. I mentioned right after the midterm that these chapters here, 16, 17, 18, to some extent 19, provide kind of a transition from the world of probability into kind of real data analysis. So chapter 19 thinks about things in a similar way, but a little bit different. So I'll define these things in a second, but roughly, we think of the statistic as being some observed value, right? It's like the percentage of people that support Barbara Boxer is an example I'm going to do. Okay, so that's a statistic. It's some. Sorry. I should define it a little more carefully. The sample or observed percentage of people that support Boxer is what we think of as statistic. That's somewhere around a parameter. We can sort of think of this as being like actual value, expected value, might be off because of chance error. And actually, the subject of chapter 19 is to discuss what we call bias. So this is chapter 19. Mostly what we're doing in chapter 19 is discussing bias. And the chapters around it all talk about chance error. So we have one chapter where we're talking about this. Bias you can think of as sort of systematic error. It's not random. It's because of some systematic problem with your sampling process. Okay? So let me define these things, and then I'll say a little more about that. Chapter 19 has basically just about no math in it because we're not able to calculate anything about bias. We can't, the standard error measures the likely size of chance error, but it's very hard to get a kind of quantitative idea of how big the bias is likely to be. All right, so let me define a few things. So a little bit like chapters 1 and 2, there are just some words that I need to get out there so we can talk about what's going on here. So the population is the group we're sampling from. So always in chapter 19, we're talking about some kind of sampling thing. We're sampling from some larger population. The group we are sampling from. So this is like drawing tickets from a box, where the population is the actual tickets. The sample is a subset of population that we know something about. Okay, so a common, this is like draws from a box. So a common setup for the sample in the population is that you do something like have a bunch of adults and you call some of them on the phone and ask them their opinions on something, okay? So that's called a public opinion poll, and it's something like taking draws from a box. It's not perfect, and I'll discuss more after break why this is not perfect. Today I just want to sort of like lay out the basic groundwork and give you an example. Okay, so there's those two, and then the parameter, which I have up there, is a numerical fact. It's typically a summary statistic, but I don't want to use the word statistic, so it's a numerical fact about population. And the statistic is a numerical fact about sample. So again, typically what we're talking about here is taking a sample from a larger population and asking the people in the sample some question. So we typically know the statistic, we don't know the parameter. Okay? So one other thing that separates chapter 19 and 21 from the other chapters is that idea. So chapter 17, 18, and 20, you can make a box somehow. It might be hard to sort of translate the problem into a box model, but somehow you can figure out what the box should look like, okay? And from that, you're asked questions like, what's the chance I win at roulette? So there's an unknown bunch of draws from this box, and you make some probability calculation telling us like what's the chance you're above some value, below some value for the sum of draws, whatever. This is unknown. We can find its expected value, and we can find its standard error, but we don't really know what happens in general. In chapter 19 and 21, it's sort of reversed. The thing we know is we know the opinions of the people in the sample. So we have some sample, draws from a box, and we ask them questions. And so we know this. We don't know the opinions of everyone in the population. But what we do know is we know how this works. Like, we know sort of about how far off we might be from the expected value. Right? The standard error tells us the likely size of the chance error. So in this world, we still can sort of get an idea roughly of how far do we think this is from that, right? Here we're doing it, we get an expected value based on the box, and we can sort of roughly say, well, we expect to be within maybe a couple SEs of the expected value, right? Here, it's backwards. We know the draws, we don't know the population, but the same kind of chance error applies, right? So this equation here maybe seems a little bit weird because the statistic is the thing we know. And what we're saying is that that statistic, whatever it is, the sample value, should be somewhere around the parameter. It should be somewhere around the population value, but it could be off because of chance error and bias. And chapters 17, 18, and 20 discuss the chance error part in depth. Chapter 19 discusses the bias, and chapter 21 kind of brings it all together. Okay? But basically, you know, it's going to feel a little bit backwards when we do chapter 19. And like I said, the lectures that I'm going to miss the lectures right after spring break, are going to mostly deal with the math in chapters 20 and 21. And then when I come back, I'll finish chapter 19 and talk about 21 a little more. Okay? I'm not done yet. So just if that sounded like I was finished. I do want to talk a little bit more and give you an example. Okay, so let's give you something a little bit more concrete here. So front page of the Chronicle this morning was a good example, so I just took it. And it was a poll with Barbara Boxer. And what they did is they took a survey, a telephone survey. I'll read you the kind of technical details. They have like a bunch of kind of explanation for normal people, and then they have in tiny little print what statisticians read, which is survey findings are from a telephone survey completed March 9th through 15th of 748 likely voters. Okay, so what they did basically is they called a bunch of people on the phone, and I'll tell you the mechanism by which they. It's sort of random how they decide who to call. It's in fact called random digit dialing. It's not perfectly random. They don't like take a phone and do this. They're using a computer to generate random numbers, and they're careful. They are careful. They don't call businesses, and they have a kind of a complicated procedure that I'll talk about after break about dealing with landlines and cell phones. And anyway, but you know, roughly think of them calling random people on the phone. So it's 748 likely voters. So what makes someone a likely voter? They ask you some questions if you don't hang up on them. And amongst the questions they ask you are like, did you vote in the last election? Are you planning on voting this time? Do you care who the senator is? Things like that, roughly. And they decide based on these questions if they think you're likely to vote in the election. So they say 748 likely voters. So they ignored the opinions of the people that they don't think are likely voters, and they get those results. So I'll just write up a little bit of this. This was done March 9 through 15. This is done by the Field Poll organization. Field Poll is a polling organization that does political polls in California pretty much, is what they do. And there's 748 likely voters. And so this early in the election season, they're talking about the November election for senator. They don't have the wording of the question exactly in here, but generally what they ask is something like, if the election were held today and the Democratic candidate is Barbara Boxer and the Republican candidate is whoever. So they'll ask different people different things. So the one I'll tell you is about Tom Campbell. Tom Campbell's currently the Republican frontrunner. So they asked about Barbara Boxer versus Tom Campbell, and they also asked about Boxer versus Chuck DeVore and Barbara Boxer versus Carly Fiorina. But I'll just give you the Campbell numbers. So this is so Boxer 43% preferred Boxer and 44% preferred Campbell. Okay. So the article is sort of about. What was the title of the article? The title of the article is "Top GOP Rivals Catch Up to Boxer." So Campbell's the only one that actually had a higher percentage than Boxer. The other two were slightly below. And then they say here again, yeah, GOP opponents catch Boxer, Field Poll says. Okay, so that's the result. And this is the number I'm going to sort of highlight. I realize these don't have to add up to 100%. There's a lot of undecided people still. But I just want to think about this as sort of a box with ones and zeros. So I'm going to consider people to either be Boxer supporters or not Boxer supporters. Okay. So can you tell me the percentage of ones in the box? So the answer is no, you can't tell me the percentage of ones in the box, right? We don't know the percentage of all likely voters in all of California that support Boxer. What we know is the statistic. The parameter is the percentage of ones in the box, okay? Let me just write that. So 43% equals the statistic. It's the percentage of ones in the sample. Okay, remember that the statistic is some numerical fact about the sample. It's that 43% of the people in the sample supported Boxer. The parameter, if I sort of say it in English, it's the percentage of ones excuse me, in the population. And it's unknown. Okay? So what we think is, we think 43% is kind of close, right? This is only interesting if those people are pretty similar, these 748 likely voters, if that's something similar to who actually will vote in the fall, right? If I took 748 people in, I don't know, classes at Berkeley, or if I took people in, I don't know what particularly liberal majors might be, or particularly conservative majors, but if I took like a specific subset of even Berkeley students, I could get very different results, right? Those would be results that would be very biased, right? So the question is, how biased are these likely voters? One question is, how biased are these likely voters? How similar do we think those are to all likely voters? And also, you might wonder if they're similar to all Californians, okay? The people that vote maybe are a little bit different than the people that, the general public of just everybody. What the field poll is interested in is who's going to vote, okay? So they don't particularly care about people that are probably not going to vote anyway. Their business is really to predict election results. So, these people are maybe not exactly the same as the people who vote. One thing about these people I'll say is, they have phones, okay? Presumably some people without phones vote. They answer their phones and are willing to talk to the field poll, which, there may be a lot of people that aren't, right? A lot of people may not be willing to talk to the field poll, but they still might vote. So you might wonder if the characteristics of these people are really similar to the other people that might vote in the fall. Okay, so that's bias. Those differences are all forms of bias. I'll get a lot more specific about that after break, but I sort of wanted to plant this idea in your head, and I think it's interesting. Okay, so I'm not here for the week after break, so I'll see you in a while when I have another baby. Okay, bye.